our today's topic would be devoted to phonons in semiconductors and electron-phonon scattering. On the previous lecture, we described how can we calculate the scattering rates and conductivity limited by electron impurity scattering in semiconductors. And it was a very useful instrument for us to treat scattering and actually the conductivity of many various semiconductors which are doped or dirty can be described within the approach that we discussed on the previous lecture. But today we will discuss a different thing. What if the semiconductor is very clean? Or what if the semiconductor is lightly doped? Now, from the course of the previous lecture, it looked that the scattering time would be infinity. The electrons would not collide the impurities and the conductivity would be very large. But actually it is not the case, because electrons can collide with vibrating atoms. At any finite temperature, the atoms would be vibrating, and it means that electrons would lose their momentum and energy when colliding with the vibrating atoms. From contemporary viewpoint, these oscillating atoms are called phonons. Phonons actually are normal oscillations of crystal that do not interact with each other, in contrast to the oscillations of individual atoms that are coupled to each other. So what is the outline of our topic? First of all, we will introduce what are atomic vibrations and phonons. Then we will speak about what is electron-phonon interaction, how an electron feels that the crystal is vibrating. And in the final part of our topic, we will try to derive the momentum relaxation time and conductivity limited by electron-phonon scattering from the Boltzmann kinetic approach that we developed previously. So let's start. The simplest model for atomic vibrations is a chain of atoms connected by springs. Actually, these springs are not real springs. This is just interpretation of interatomic interaction energy, which appears due to Coulomb effects, due to interaction of atom in its neighboring electrons, and so on. But the only reason to consider the spring is that when atom is deviated from its equilibrium position, which is denoted here by R1, R2, R3, and so on, when it is deviated from its equilibrium position by amount of U1, U2, U3, and so forth, then the energy of such a displaced atom would be proportional to the square of the displacement. Just like in the theory of spring, which is expanded according to the Hooke's law. So just by analogy with a spring that has a potential energy of W equals kx squared divided by 2, here the system has a potential energy that is proportional to the squares of these displacements. And so this allows us to consider the atoms in real crystals like balls connected by the springs. So our goal today will be to try to find such oscillations, such change of the coordinates, according to which these vibrations would be decoupled, according to which these vibrations would be non-interacting. So we start by writing the total energy of the system, which I denote by the letter H in analogy with the quantum mechanical Hamiltonian, but this is for the first time a classical consideration. And the total energy of the system is the summation over atomic indices. Here we have the kinetic energy, which is proportional to the velocity of each atom squared divided by 2. This is the kinetic energy of each individual atoms. Please mind the dot over the displacement, which means the velocity, and there is the the potential energy of interatomic interactions, which I denote by gamma divided by 2. Gamma is the analog of the stiffness of each spring. To make a distinction with this classical analogy, we denote it not by K but by gamma. We will reserve K for another purposes. And here the displacement of each atom is subtracted from the displacement of the previous atom. This form appears because if we displace two atoms simultaneously, then the spring would not exert any tension. It would be neither compressed nor expanded, so no interaction energy would appear. But if we displace the atoms by a different amount, like here the displacement is weak, but here the displacement is large, then the spring would be compressed, and then there would be some energy stored in this compression. And for this reason we have the difference between the displacement of neighboring atoms. Here the summation runs from -infinity to +infinity over all the possible atoms. And so why would we need phonons? Why would we need something else? Why cannot we derive the mechanics of the crystal just from this? Because this form of energy is inconvenient. The oscillation of each atom is coupled to the previous atom or to the next atom. In other terms, the oscillations of neighboring atoms do not contribute to energy additively. There are cross terms like UE, UI -1 when we try to expand this product. And we need to find some transform for these displacements so that the kinetic energy is the sum of independent terms. This is the main problem of crystal mechanics. So let us try to do this. Well, the energy is this product. Sorry for the defects in this PowerPoint. This sign stands for the time derivative. This is the velocity. Let's try to find the transform of the coordinates that diagonalizes this energy form. So to do this, we try to express the oscillation of each individual atom as a combination of plane waves. We actually know that from general physical experience, like we have a series of balls connected with springs, and we pull one of the balls, then the wave will appear in the system. So let's try to find such transformation in the form of the waves. So the displacement of each atom is expanded as a sum over all possible wave vectors of the waves. Each has the amplitude u with subscript k and the running nature, like exponent of I k r if minus omega t. So it runs along the crystal. Actually, to compute the energy, we will need real functions. The vibration amplitude should be real. Therefore, we add complex conjugate to this expression. It would be important for us, and this complex conjugate has the exponent with the opposite sign. So now our goal is to plug this representation here and to see what happens, whether it indeed is decoupled into the sum of independent vibrations. Let's try to check. So we plug this into this. What terms we deal with? And of course we will need to average this expression over time, because we need to know only the time average for only the time average for this expression. Here we have some results advanced, but let's try to derive it relatively carefully. So what happens if we find the product of ui dot multiplied by ui dot? When we differentiate this, we get the sum over wave vectors uk minus I omega k exponent to the positive power. Let me not write it in detail. Then here we have plus uk complex conjugate I omega k exponent to the negative power. And we will need it, we will have to multiply it by the same thing. Here the index of summation should be generally different, let it be k prime, and here we have minus uk prime I omega k prime exponent to the power plus I something, and here is plus uk star I omega k exponent to the power of minus something, and we will have to average it over the time. The expression looks terrible, but actually what is important here, that when we make time averaging, the exponents generally cancel. The only situation that they do not cancel is that they have exactly compensating phases. So this can appear if we multiply this by this, or if we multiply this by this. So here the exponent is with positive power, and here the exponent is with negative power. And the other necessary condition is that they do not cancel when we make time averaging, is that the indices k from here and here do coincide. It means that if the frequencies of oscillations are the same in this term and in this term, otherwise if the frequencies do not cancel each other, then the time averaging would yield 0. So the final result after the time averaging is greatly simplified. It is sum over individual vibrations minus I omega k multiplied by plus I omega k uk star, and no exponent. And the factor of 2 comes from the fact that we have two possible non-canceling combinations. And the final result is that we have two sums over independent wave vectors, oscillation frequency squared, multiplied by squared modulus of the wave amplitude. So here we have the desired form. Actually, we have proven that the kinetic energy of the atoms is equivalent to the kinetic energy of individual waves with distinct wave vectors uk. We can actually write it in a more concise form, like 2 sums over k modulus of time derivative of wave amplitude squared. And I use this representation here on the lower board when I try to write the kinetic energy. But the most complicated stuff appears when we try to find the potential energy. The potential energy involves two neighboring vibrations, and it looks that it is more complex. So let's clean it and see what happens with the kinetic energy. Here we will need the terms like oscillations of ith atom minus oscillations of a neighboring atom. The advantage of the wave representation here is that the oscillation of ith atom differs from its neighbor only by the phase, because the shift in the position is encoded only here. So if we go from ith index to I minus first, then we only shift the radius vector here. So that if we take unity amplitude of the first atom oscillation, then its neighbor would oscillate with a phase delay of ik r ith minus I ri minus first. And here we have the oscillation of the wave, uk exponent to the positive phase. What we do with this complex conjugate term, we do the same, but the phase shift is just opposite. So for the complex conjugate, we have 1 minus exponent to minus ik ri minus ri minus first uk star exponent to the negative power. So it is very good. The difference between the neighboring atomic sites can be denoted by A. A is the interatomic separation here, and the form of the difference of neighboring displacement is sum over wave vectors 1 minus exponent to ika wave amplitude exponent to the positive phase, and sum over k 1 minus exponent with negative phase shift uk star exponent to the negative phase. Now we will need to take the square of this modulus and average it over time. But the tricks here are the same as in the potential energy. So many terms would cancel. And I will write this result quite quickly using the same hints. So if we take this squared and averaged over time, then we would have the only non-canceling terms would come from this multiplied by the complex conjugate with exactly compensating phases. And there will be two such terms. So there will be two terms of the form sum over k 1 minus exponent to ika 1 minus exponent minus ika uk star, and the phases have cancelled upon time averaging. This expression is purely real. Actually, we can simplify it in our mind. This is 2 minus 2 the sines of Ka. So the term that we need for the potential energy has greatly simplified. It is sum over wave vectors of 2 minus 2 cosine of Ka squared modulus of the wave amplitude. So we have actually achieved our desired goal. The potential energy of crystal vibrations is now a sum of individual non-interacting oscillations that are encoded by the wave vector k. If we plug it into the expression for the total energy, then we would have separate kinetic energies and separate potential energies. This representation is called phononic representation for the total energy of the vibrating crystal. Please ask some questions, as many questions as possible, please. Maybe if you don't understand or didn't catch the maths, maybe you will ask something about physics of these crystalline vibrations. Don't be shy. Okay. If you are shy, let me try to probably explain simpler things. Maybe you will be familiar with that. So let's try to find some usefulness from these representation. So we have transformed the total energy of vibrating crystal as a sum over individual vibrations with the velocity uk dot squared modulus and the potential energy, which is proportional to the wave amplitude squared, and some strange terms. Actually, we can try to see on this in comparison with some simpler oscillators, like let's try to compare it with a ball on the spring. So if we compare it with the ball on the spring, then it has a simpler energy, which is the kinetic mx dot squared divided by 2 plus k x squared divided by 2, and its vibration frequency is just the square root of stiffness divided by the mass. Vibration frequency would be the square root of k divided by m. And as the form of the total energy is the same, we can think that the square root of this term divided by this term would be also something like vibration frequency. It is just if the two objects are mathematically the same, then the properties can be described in the same language. So let us try to write the oscillation frequency of this phononic model. It is square root of a prefactor before the displacement squared. It is 2 multiplied by 2 minus cosine of Ka, and the prefactor between or before the velocity squared, the mass. Here we should also have the stiffness gamma. If we re-express this as using the formula 1 minus cosine Ka is 2 sine square Ka divided by 2, we will get a very nice result for the oscillation frequency for an individual phonon. It is presented on this board. The frequency of phonon with wave vector k is proportional to the square root of stiffness divided by mass. This is just like in a simple mechanical oscillator, and some factor that depends on k. The meaning of k is the wave vector. If we expand this at small values of k, then we will get a linear relation. The dimensionality for this square root of gamma divided by m multiplied by interatomic spacing is the speed, and this is natural to call this as a speed of sound, because sound is nothing but atomic vibrations in solids. And if we try to plot this is called the dispersion law, or the dependence of frequency on momentum, omega versus k. We will get this well-known sound-like behavior. Sound-like means that that on initial stage the dispersion is linear, omega equals sk, but when we have the wave vectors very large, so that the wavelength is comparable to interatomic periods, then there is a downward bending of this curve. So this is one of the most important results of classical vibration theory in solids. We managed to find the oscillation frequency. But now there is one more important result which can be inferred from the quantum theory. In classical theory, this is the total energy of vibrating atoms expressed via the wave amplitudes. In quantum theory, the wave amplitude and the velocity of change in this amplitude should be considered not as numbers, not as some quantities that can be measured simultaneously, but they should be considered as operators. And this should be considered not as a classical total energy, but as a quantum Hamiltonian operator. As these quantities, the wave displacement and the velocity of this displacement cannot be measured simultaneously. And actually this procedure, the procedure of finding quantum eigenfrequencies for this Hamiltonian, can be done with relative ease because it's a Hamiltonian of harmonic oscillator. The eigenvalues of this oscillator are very well known. These are the integer numbers of h omega, where h is the reduced Planck's constant, and there is some extra factor of 1/2, which appears due to zero-point motion in these oscillations. And actually, the amplitude of the wave cannot take on any values. It can be only integer of h omega plus 1/2. And this quantity nk is called the number of phonons, the occupation number of phonons. Actually, if we try to pump the solid with sound, and if we try to shake it, the number nk would be growing the more energy we pump into the system. Actually, the energy is proportional to the number nk. But even if we don't pump the solid intentionally with sound, there is some fluctuating number of phonons which appears due to the finite temperature, and this is given by the Bose-Einstein statistics. So nk is, nk should be given by the Bose statistic 1 divided by exponent of h omega k divided by kt minus 1. If we try to consider the wave vibrations semiclassically, when the number of phonons is very large, we can write that the amplitude of the wave uk is proportional to the square root of occupation number, nk to the power of 1/2, and multiplied by some quantity with the dimensionality of coordinate, square root of h divided by m omega. Можно, пожалуйста, камеру поближе, а то я может, меня будет не видно, но доску будет более видно. Okay, so this is the semiclassical wave amplitude. It is proportional to the square root of occupation number. This representation is valid actually at high temperatures when all occupation factors are large. This is enough for the theory of phonons by themselves. Now this is actually setting these preliminaries would allow us to calculate the internal energy of oscillating solid, the heat capacity of solid at finite temperature, but this is not our goal. This can be found in some textbooks on general physics. Our real goal would be to see how an electron moving in a crystal oscillates with these phononic vibrations. The physical question may appear why electrons do feel the phonons. Actually, the simplest model that we can consider is a double quantum well. These quantum wells can be considered as models of atomic nuclei that attract electrons, and if they are located at some specific positions, so that the difference between these two in equilibrium is A, then the energy of an electron that is located in this double quantum well would be at some value E0.
Could you explain how we can take the expression in one line of previous two lines?
This?
Yeah.
How can we derive? Okay, that's actually a very good question. How can we derive this? This is the problem of finding the amplitude of vibrations from quantum classical correspondence. We know that for a harmonic oscillator, the average kinetic energy of vibration equals to average potential energy of vibration, and when we derive it, we can forget for a while about this because this is relatively complicated, but we can multiply this by 2, and so what we will get as a result, that's a great question, because you noticed one of the misprints here. The total energy is twice the average kinetic energy. When we re-express the kinetic energy, we use the fact that U dot K is omega K UK, if we take it by modulus, and what we have as a result is 2 omega K squared M UK squared modulus is H omega K MK. This is approximately valid when in the classical limit when all nth are large. So, and this brings us to the expression for the oscillation amplitude with extra correction factor with square root of 2 in the denominator. That's great that we switched on the sound because you found a misprint. Any more questions? Did I answer your question? Okay, so hope we can continue. Why electrons interact with phonons? Actually, this energy of electron located in model crystal depends on the distance between the wells, and you can actually see it on a simplest example on the simplest example of electron in a double delta well. This is an exactly solvable model. You can derive the energy of the lowest level E0 versus interatomic separation A, and at infinity the wells would be non-interacting, and as we approach the wells to each other, then the level would be deepened due to the interaction, and then it would rise again because it tends to a level in a single delta well with doubled strength. So the dependence of energy level on the displacement, on the relative displacement between two wells, would look something like that. And this would correspond to the equilibrium position. So an electron in solid feels the position of the atoms, because when we change the position of the atoms, we change the spacing between the quantum wells that mimic the atoms. And it is instructive that the electron feels only the relative displacement. Indeed, if we displace one well to the right and the second well to the right also, so that the interwell distance remains the same, the energy would not feel that, because this means that we have shifted the crystal as a whole, but the observable quantities do not know about it. So the energy levels would be sensitive only to the relative shifts of the atoms. In this case, they would be sensitive only to U1 minus U2. Now, let's try to think what happens if the crystal is characterized by a continuum displacement vector. So if the atoms near position R have the displacement of U versus R, and then the energy of this displacement that is seen by electron should be insensitive to the displacement as a whole, but can be sensitive to the derivatives of this displacement. And the most general form that we could imagine for the electron-phonon interaction is that it is the power expansion over displacement vectors. They can be, in principle, the first power, but it would mean that the electron is sensitive to the displacement of the crystal as a whole, and it should not be the case in realistic crystals. Then there should be the first power of displacement, the first derivative of the displacement, and it should be a scalar. But the only operation that acts on a vector and produces a scalar, the only differential operation, is taking the divergence. So the interaction energy should be proportional to the divergence of displacement field. The constant here, d, is called deformation potential. It has the dimensionality of energy, of electron volts, and called deformation potential. Of course, there can be some higher order terms of displacement, but if d is non-zero and the crystal symmetry allows the presence of these divergent terms, then the higher order terms of displacement would be also ignored by us. So we will consider the electron-phonon interaction potential in the form d divergence of u, where u is the displacement field, d is the deformation potential, and the physical meaning of this expression is that electron energy in a system of wells is proportional to the relative displacement of these wells. I hope this is quite physical. Actually, d is to be determined either from these model problems or by comparison with experiment or by some first principle calculations. Now our goal would be to express our expression for displacement in terms of a sum of individual phonons and see how it looks in real space and which transitions can it induce in electronic system. Our final goal is actually to find how an electron with some momentum p collides with Our final goal would be to consider how an electron with momentum p collides with a phonon with a chain of vibrating atoms and transfers to the state characterized by momentum p prime. So we will need to consider the probability of this scattering process. So we will inspect the interaction energy and to see which matrix elements it has non-zero between the electronic plane waves. These matrix elements would show us the possible transition probabilities in the system. So let's try to do it in more detail. We take the expression for the displacement in terms of independent phononic waves and introduce it into the expression for the divergence. This is the interaction energy of electron with a set of phonons seen in the real space. In the real space characterized by radius vector r. Now we would like to inspect which non-zero matrix elements it has between electronic states. Electronic states in a free crystal are characterized by plane waves. The plane wave state with momentum p is just the de Broglie wave normalized to the volume of the crystal, exponent to IPR divided by h. And we will see whether an electron can have some hopping amplitude from the state characterized by p, which is the initial state, to the final state p prime, which is the same plane wave but with a different momentum. Let us evaluate the matrix elements of this interaction Hamiltonian between two plane waves with different momenta. So what we need to consider is the matrix elements of the form the interaction P, and in extended notation it is the integral over the volume of the crystal of the product of these two plane waves and this interaction potential. What we get from the product of these two plane waves, we have exponent I momentum, my initial minus momentum final, multiplied by r divided by h, and from interaction potential we have the sum over k d I k u k exponent of I k r minus omega t and plus Hermitian conjugate. What is remarkable here? We have one plane wave, we have two plane wave exponents for the electrons, and we have one plane wave exponent for the running phonon. If we integrate it over volume, the phase factors for these exponents would generally cancel each other because these are rapidly oscillating functions, and being integrated over the whole volume, they would yield zero. The only opportunity to not produce zero is that the phase factors for these exponents cancel exactly. This can happen only when p minus p prime equals hk, or in other terms p equals p prime plus hk. This means that an electron with momentum p P has emitted a phonon with momentum k. This corresponds to the emission process. And there is another possibility it comes from this Hermitian conjugate term. Here we have the phononic exponent with a different sign, and it corresponds to a different sign here, to the different sign in the momentum conservation law. It can happen that that an electron would absorb phonon. So these two non-zero possibilities physically correspond to emission and absorption of the phonons. And when transforming further this expression, let's write the following rule. If we integrate some exponent with combination of wave vectors p minus p prime minus hk r over the volume, we get either 0 when the momentum conservation law is not fulfilled, if p is not equal to p prime plus hk, or we obtain the volume of the crystal if the momentum conservation law is fulfilled. All these rules can be written in a shorthand notation if we use the so-called Dirac delta function. The result is plotted. The result is plotted here in my shorthand notation. The result for evaluating this matrix element. Here the term corresponds to the process when final momentum equals initial momentum plus phonon momentum. It means an electron has absorbed a phonon from the field and passed to the state characterized by momentum p prime. And this term corresponds to emission. The initial momentum is the final momentum plus phonon momentum. The exponents in this term or the time exponents are also different. They have different sign in this oscillation frequency. So these results are very physical. When we have expanded the crystal vibrations into the plane waves, we have seen that they can induce transitions when electron either absorbs a phonon or emits a phonon. Now we are almost ready to plot some pictures for this, because when writing the collision integrals, it would be instructive to present these results in figures. So here the first term corresponds that electron shown with a straight line absorbs a phonon with momentum k and passes to the state with momentum p prime equals p plus k. Here the process is the opposite. An electron from the state p emits a phonon and passes to the state p prime equals pi minus k. This is the process of emission. These processes would contribute to the collision integral, and this part of the collision integral is called outgoing part. Outgoing part means that the state with momentum p is depopulated. It can be depopulated either via absorption of a phonon or via an emission of a phonon. But all these terms correspond to the depopulation of state with the momentum p. We can write it for the first time quite symbolically. The collision integral, namely its outgoing depopulation part, is proportional to the probability that initial state is occupied. This is characterized by distribution function fp. The probability that the final state is empty, which is characterized by distribution function 1 minus Fp. And there could be two possibilities. Either we can absorb a phonon or we can emit a phonon. All these probabilities are given by Fermi-Golden rule. Fermi-Golden rule, let me remind you, is written in the form: the probability of transition in unit time is 2 pi divided by h multiplied by the matrix elements of the interaction Hamiltonian between initial and final state squared, and the delta function of initial energy minus finite energy minus plus driving frequency. The driving frequency can have either positive sign or negative sign, as we have seen in the previous slide. So we can now take the interaction matrix elements from the previous slide and write the delta function corresponding either to emission or absorption processes. What we will get is that the outgoing part of the collision integral would contain two possible conservation laws. One conservation law corresponds to the absorption of phonon. Initial energy of the system is the energy of electron and energy of a phonon, and final energy of the system is the energy of an electron. And emission process with the negative sign before the phonon frequency. The matrix elements for emission and absorption can be taken from the previous slide. Let's write it once again here. These interaction matrix elements are IK UK multiplied by deformation potential. In classical theory, where the vibrations of crystal are considered classically, we do not distinguish between absorption and emission, and the absorption and emission matrix elements are the same. I see a question in the chat: is it electron-phonon or electron-photon? Everywhere we are speaking about phonons. Phonons means crystal vibrations, quanta of the sound waves. If I told photons, then it is my mistake. It is all about phonon interactions. So in classical theory of crystal vibrations, UK is the wave amplitude, and we don't differ between absorption and emission. And for UK, we can write the classical type expression: square root of h divided by 2 atomic masses, oscillation frequency, occupation number to the power of 1/2. And this would be quite okay. But in quantum theory, if we consider the quantized phononic oscillations, this should be slightly changed. What are the requested changes? If we consider classical vibrations versus quantum vibrations, once more, in a classical theory, the interaction matrix elements for absorption and emission are IK unit vector in the direction of phonon propagation multiplied by square root of h divided by 2 m omega multiplied by occupation number to the power of 1/2. In quantum approach, there are some differences between emission and absorption processes. Can someone give me a hint? What is more probable in quantum theory? To absorb a quantum of sound or to emit a quantum of sound?
The emittance is more probable because the matrix element will be there will be square root of n and square root of n minus 1 the other way.
Well, it is very good. This is a very good answer. I prefer here the physical interpretation, like when we have void, we have no oscillations at all. We, for example, know that the atoms in excited state can decay. They can emit photons from our common experience, and no field should exist at all. So if no field exists at all, no vibrations, no oscillations, emission is always possible. But absorption requires something to be absorbed, and there is some difference in quantum theory. The interaction matrix element for emission, as correctly mentioned, should be corrected. It should be corrected so that emission would be possible every time, even if we have no vibrations. So here we should have square root of nk plus 1 reserved quantum for emission. And for absorption, we would have the same. Interaction matrix element for absorption is IK. Actually, it has a different sign, but it doesn't matter much. The absorption needs something to be absorbed. So here we have square root of nk. In quantum theory, the probabilities of emitting and absorbing a phonon are different. This can be important at relatively low temperatures when the occupation numbers of phonons are low, but at high temperatures and at room temperature, this difference is not so important, and we can treat the emission and absorption with a quasi-classical approach. Now we introduce these expressions into the collision integral, and we have this outgoing part. This is our final result, the first line. Okay, to summarize, the first line corresponds to the emission. The first line corresponds to the absorption of phonon, and it needs something to be absorbed. So here is nk, and this line corresponds to the emission of phonon. Emission can happen every time. Here we have nk plus 1. Here is the matrix element for the interaction, and I have explicitly taken into account that the wave vector k that appears when we simplify the divergence of collision integral, the wave vector of phonon equals the difference of electronic wave vectors in initial and final states. Now we could make the same for the ingoing part of the collision integral. So we have seen the processes that depopulate the state P and populate the state P prime. Now we need to reverse the picture to make a full collision integral that has also ingoing part. I summarize it in this picture. This I think is quite useful, and you can plot it by yourself. You will have it in the presentation that I have in a Google Drive folder. So the outgoing part of the collision integral have this absorption process and emission process. The ingoing part into the state P corresponds to flipping P and P prime. So we start from P prime and go into P. But not only this flipping should be made, but also the flipping of the phonon line. So absorption becomes emission, and emission becomes absorption. So to make this detailed equilibrium, we also write the ingoing part of the collision integral that populates the state P and depopulates the state P prime. What are the differences between these two? The difference is that here this ingoing part is proportional to the probability that the state P is empty and the state P prime is occupied. And the difference here is that absorption has become emission. So we have changed the all n population factors into the n+1 population factors. I think we don't have much time left, but a good home task for you would be to plot these pictures denoting the population and depopulation of state of electronic state P, and to write once more the collision integral with all necessarily Fermi and Bose functions. You cannot remember this interaction matrix element because it can be looked up from the textbook, or it can be rederived. Actually, it depends on the type of the phonon, either it is optical or acoustic, but the most important factors are the Fermi factors here and the Bose factors here. And a good task would be to substitute the equilibrium Fermi functions and equilibrium Bose functions into this collision integral, and to prove that it yields 0 after all simplification. It means that when both electrons and phonons are in thermal equilibrium, they don't collide with each other on average, and the finite collision rate appears only when we deviate something from equilibrium. The simplest case of this deviation is when we drive the electrons with DC electric field. So we have little time left, and I will sketch the final calculation that we would make up to an end on the next lecture. Our goal would be to find the conductivity limited by electron-phonon scattering. All these outgoing and ingoing parts of the collision integral look terrible, but they can be greatly simplified due to the following reasons. First of all, the energy lost by electron in a single act of electron-phonon collision is quite small. Let the lost momentum be q. Then the phonon energy is hq multiplied by sound velocity. The electron energy is p squared divided by 2m. So if the lost momentum is order of momentum itself, when q is order of initial electron momentum and is order of thermal momentum or Fermi momentum, then we can write down the following estimate. This is roughly sound velocity multiplied by thermal momentum, and this is the thermal momentum squared divided by 2 masses. The ratio here is roughly sound velocity multiplied by thermal velocity. And in some situations, when the semiconductor is relatively at cold temperatures, these can become comparable. But when semiconductor is cold, it becomes degenerate. So we should more carefully write something like that: sound velocity divided by Fermi velocity of electron. The typical numbers here are that Fermi velocity is roughly 10 to the 5th, 10 to the 6th meter per second, while sound velocity is roughly 10 to the third, 10 to the fourth meters per second. And this is generally much less than unity. So the energy lost by electron in a single act of electron-phonon collisions is very small, and we can neglect the phonon energy in these delta functions, which characterize the energy conservation. The second simplification is that in most situations we can treat phonons classically, namely at high temperatures. When the temperature is high, the exponent in the Bose function is close to unity because its exponential factor is much less than 1, and when the temperature is high, this simplifies to kT divided by energy of phononic quantum. But this means that the difference between absorption and emission is completely washed out. It is washed out both when we consider energy conservation, because energy is almost not lost, and it happens when we consider the probabilities. The probabilities of absorption and emission are almost the same at relatively high temperature. With these assumptions, the collision integral is simplified, because all quantumness, all the complexity came from the difference between absorption and emission. But when this difference is neglected, the collision integral becomes very, very simple. These simplifications will be done to the end in the next lecture, and we will derive momentum relaxation time due to electron-phonon scattering, and this will allow us to find the phonon limited conductivity. Now I'm ready to answer any of your questions, probably on general physics or on math, on anything, please.